Welcome to Study Loop.
So, in this question, if we see, air is heated in a duct during subsonic flow until it is choked. For specified pressure and velocity at the exit, the temperature, the pressure, and the velocity at the inlet have to be found out. These are the three quantities that we need to find out. Okay, so let's see how does it go. So in order to carry forward this question, we have to take certain assumptions here. So the first assumptions associated with Rayleigh flow is that it should be a steady flow. It should be a one-dimensional flow of an ideal gas. Ideal gas should be there. That is important. With constant properties. Constant properties should be there. Then we should have a constant cross-sectional area. This is also very important. Cross area of the duct and negligible friction should be there, and that is only valid for this case. So we take here certain properties also, and the property of air that we have to take is K is equals to 1.4, Cp equals to 1.005 kilojoule per kg Kelvin, and our R equals to 0.287 kilojoule per kg Kelvin. So now when we are doing the analysis of this question, we'll see that the sonic conditions exist at the exit. So sonic conditions are there at the exit. So the exit temperature, we have to find that out. So how will we find out the exit temperature? With the formula C2 equals to V2 upon ME2, which is equals to 680 meter per second. So C2 here is equals to K root of KRT2, and that is equal to 680, right? So from here we find out that T2 is 1151 K. So this is the exit temperature that we have, 1151 K. This is the first thing that we require. Now we have to find out the exit stagnation temperature. Okay, so stagnation temperature is equals to TO2 equals to T2 plus V2 square upon 2 Cp. Now keeping all these values, we get the value as 1831 Kelvin. Now the inlet stagnation temperature, this is the exit one. Now inlet stagnation temperature here is from, so when we see the inlet stagnation temperature that we have to find out is from the energy equation, and the energy equation tells us that Q is equals to Cp into T02 minus T01. Now from here we have to find out T01, that is the inlet stagnation temperature, right? So from this we have T01 equals to T02 minus Q upon Cp, and that is equals to 1314 Kelvin. This is the inlet stagnation temperature, and this was exit stagnation. So exit is T02 and inlet is T01. Got it? Okay. Now, the maximum value of stagnation temperature, okay, the maximum occurs when the Mach number is equal to 1. And its value in this case is T02 since the flow is stopped. Now, therefore, T0 is equals to T02 maximum 1 equal to 1381 Kelvin. Then the stagnation temperature ratio at the inlet and the match number corresponding to it are from table A34. Take table A34. From that we get the values. So if you see T01 upon T maximum, that is 1314 Kelvin upon 1381 Kelvin, and that is equals to 0.9516. So for this we have the match number to be 0. Approximately 778. Okay, so this is the approximate match number that we have for this condition. Now, now we are taking these conditions so that we could get the requisite values that we are required to have. Okay, so here MA1 equals to 0.7779, T1 upon T star equals to 1.018, P1 upon P star 1.301, V1 upon V star equals to 0.7852. Now MA2 equal to 1. Then we have T2 upon T star equal to 1. P2 upon P star equal to 1. And V2 upon V star equal to 1. So consisting of all these values, we can now find out the requisite temperature, the pressure and the velocity also. So let's see. So we see that T2 upon T1 is equal to T2 upon T star divided by T1 upon T star. So from this we get T1 to be 1172 Kelvin. Now similarly, we have P2 upon P1, and from that we get P1 to be 351.3 kilopascal. Now the next one, that is for the velocity, we have V2 upon V1, that is equals to, similar to this, from here we get V1 equal to 533.9 meter per second. So consisting of all these values, we will get the requisite inlet temperature, pressure and the velocity. I hope you understand.